Today we are going to discuss the adiabatic processes. In the previous lecture, we talked about how to get the work done in an isothermal process. Adiabatic processes are the one in which no heat is allowed to either enter or leave the system. And we will develop several equations and show that when we want to calculate the work done in an adiabatic process, we do not actually need to work through pressure and volume. If it is a pressure volume change, we can actually work through changes in internal energy. The reason is that let us recall that the change in internal energy delta U is equal to Q plus W, and for an adiabatic process Q is equal to 0, therefore, delta U is equal to W. So, in order to calculate work, if I can simply calculate the change in internal energy, that does the work, that does the job of calculating the work. Let us take a look at the slide. Since in order to calculate the work, we need to calculate the change in internal energy, let us see how we can do it. This is a plot of temperature versus volume, and this is how the temperature will fall when the volume increases. Why the temperature falls when the gas expands under adiabatic conditions, or why the temperature will increase when the gas is compressed under adiabatic conditions? The reason is, if you allow a gas to expand under adiabatic conditions, we are not allowing any heat to either enter or leave the system. Therefore, any work which is done at the cost of internal energy. That means, if the work is done by the system and you are not allowing any heat exchange, and then during expansion the internal energy of the system must decrease, and since the internal energy will not just depend upon the changes in the volume, and since here we are not allowing any heat exchange, therefore, the temperature of the system must fall during expansion, and that is what is seen here in this figure. You see, when the volume is changing from V I to V F, the temperature changes from T I to T F, there is a fall in the temperature. And if I divide this process into two steps, that is a step 1, where I keep the temperature constant, it remains constant T I, but the volume changes. And since we will refer to ideal gases, the internal energy does not change in an isothermal expansion. So, U remains constant. And the second step can be, now let the temperature change from T I to T F and the volume is remaining constant, and here I can use delta U is equal to C V times delta T. This is how you can change, you can calculate the change in internal energy. Let us take a look at step by step. This is the first law of thermodynamics, and since Q is equal to 0, I can set W is equal to delta U. So, calculations of delta U become very important. From the definition of the heat capacity at constant volume. Cv is equal to dou u by dou t at constant volume, and this can be rearranged to get delta u for a finite change, which is Cv times the difference in the temperature. And this calculation requires the knowledge of final temperature, the knowledge of initial temperature, and the value of the heat capacity. Now, we will discuss how to calculate the work done during an adiabatic change, and most of my discussion, unless I specify it, my discussion will refer to ideal gases. Let us talk about the work of adiabatic expansion, or if I call it as adiabatic pressure volume work. Once again, let us recall the first law of thermodynamics. This will be important throughout the discussion. Du is equal to dq plus dw, and work done will be equal to integration of du from initial state to final state, because dq is equal to 0, and instead of du now I write Cv times delta t, and if Cv is independent of temperature, it can come out of the integral, and what we get is this expression, that W is equal to Cv times delta t. So, in order to calculate the work, what we need is the information on delta t, and we need the information on heat capacity at constant volume. This is how we calculate the work of adiabatic expansion. So, the work done during adiabatic expansion of a perfect gas is proportional to the temperature difference between the initial and final state. Remember that this work is being done at the cost of internal energy. Therefore, this W will be same as delta U, and that conclusion we must remember, that in adiabatic changes work is directly equal to changes in internal energy. Let us consider this special case. Under what conditions the expansion of a perfect gas is simultaneously both adiabatic as well as isothermal? Let us try to solve this question. As I said that the mathematical form of the first law of thermodynamics is very important in addressing such problems. Du is equal to dq plus dw. Since process is adiabatic, dq is equal to 0, and for a finite change I can write delta u is equal to w. For delta u I can write n times CVm times delta t we just discussed, and w is minus P external times delta V. From this step to this step, what we assumed is that the process is adiabatic. From this expression, I get delta T is equal to minus P external times delta V divided by N times CVm. So, if I know the external pressure, changes in volume, and the heat capacity, I can calculate the change in temperature. From this expression, I can immediately tell that under what conditions the process is going to be isothermal. Let us take a look at the slide. This is what I just described, that du is equal to dq plus dw, and then immediately for an adiabatic change I can write that work done is equal to Cv times delta T. Remember that Cv is the heat capacity for a given size of a substance, and this Cv is equal to N times Cvm, number of moles times molar heat capacity. So, there should be no confusion when I write Cv or I write Cvm. That is why when I discussed here, I talked in terms of Cvm. So, delta T will be equal to 0 if the P external is equal to 0. So, here you have the answer that when the gas expands against 0 pressure, what is that 0 pressure means? Expansion in vacuum. So, you have the conditions. We started with an adiabatic process and we found out that if external pressure is equal to 0, then there is no change in temperature. Therefore, expansion in vacuum is simultaneously both adiabatic as well as isothermal. Next, let us now talk about the special case of reversible adiabatic pressure volume changes. Remember that when we were talking about isothermal expansion of perfect gases, we showed that the maximum work is available from the system when it is operating under reversible isothermal conditions. And now let us see what happens if we remove that condition of being isothermal and carry out the process under adiabatic conditions. Here we are going to derive two equations, Vf Tf raised to the power c is equal to Vi Ti raised to the power c, where this c is the ratio of heat capacity and Nr. The second equation that we are going to derive is Pv gamma is equal to constant, where gamma is the ratio of heat capacities at constant pressure and constant volume. Very easy derivation. Let us see how to get it. Once again, du is equal to dq plus dw, and adiabatic, since we are talking adiabatic changes, dq is equal to 0. So, I have du is equal to dw, and du is n times Cvm times dt, and dw is equal to minus P dV. I am keeping P because the process is reversible, and this I can say minus N R T by V into dV. Now, using these two, I can write that Cvm into dt by T is equal to minus R into dV by V. Or I can write this as Cvm by R into dt by t is equal to minus dV by V. And if I now integrate from T I to T f, V I to V f, then what I get is, I will write here that C V m by R log T f by T I is equal to log V I by V f. I am consuming the negative sign. Now, from this equation, the equation that we just derived, that C V m by R is log T f by T I is equal to log V I by V f. I can write log T f by T I is equal to log V I by V f raised to the power C V m by R. And then I can further rearrange this, that is T f by T I is equal to V I by V f raised to the power C V m divided by R, or I can write this as V f T f raised to the power C is equal to V I T I raised to the power C with C equal to C V m divided by R. So, now let us look at the second equation, that P V gamma is equal to constant. This is what we need to now derive. Let us see now how to get that equation. That is very easy. P f V f is equal to N R T f, that will anyway be valid, and P I V I is equal to N R T I, that will be valid. So, from here I can write P f V f P I V I is equal to T f by T I. Okay. So, therefore, T f by T I is equal to, we have V I by V f raised to the power R by C V m. Now, when I rearrange P f V f over P I V I is equal to V I by V f raised to the power R by C V m. From here, I get Pf Vf raised to the power 1 plus R by CVm is equal to Pi Vi raised to the power 1 plus R by CVm. Now, 1 plus R by CVm is equal to CVm plus R divided by CVm, and this is equal to CPm, because CPm minus CVm is equal to R divided by CVm, and I call this as gamma. So, therefore, my equation now becomes Pf Vf gamma is equal to Pi Vi raised to the power gamma. Now, let us go back. What we have in this is Pv gamma is equal to constant, where gamma is the ratio of Cp and Cv. So, what we have is CVm by R log Tf by Ti is equal to log Vi by Vf. This rearranges to log Tf by Ti is equal to R by CVm into log Vi by Vf. This further rearranges to Tf by Ti is equal to Vi by Vf raised to the power R by CVm. This I can rearrange now to write in this form, that Vi upon Vf is equal to Tf upon Ti raised to the power CVm divided by R, which suggests the equation Vf Tf raised to the power C is equal to Vi Ti raised to the power C, and this is the equation that we were planning to derive, with C is equal to Cv by Nr or Cvm by R. Now, let us see under what conditions the work available from the system is more. Is it under isothermal conditions or under adiabatic conditions? Let us take a look at this figure. Let us take a look at the green curve, which is according to PV is equal to nRT. See, for an ideal gas, PV is equal to nRT. So, if the process is isothermal, temperature is constant, then the pressure is inversely proportional to volume, because N is constant, R is constant. And that is what you see in this green line, that as the volume increases, the pressure decreases this way. Now, for an adiabat, we just showed that PV gamma is constant. That means P is inversely proportional to volume raised to the power gamma, where gamma is equal to ratio of Cp and Cv. Cp since is greater than Cv, Therefore, gamma is always greater than 1. Now, if gamma is greater than 1, and then if you compare this versus this, here with increase in volume, the pressure is going to decrease more sharply, because gamma is greater than 1. And that is what we see in this blue line, which is for a perfect gas adiabat, that as the volume increases, the pressure is decreasing more sharply. And then, as we discussed in the previous lectures, that the area under the curve between the specified limits represents the work available from the system. So, obviously, here the area under adiabat between V I and V f is less than the area under an isothermal case. Therefore, more work is available from the system when the gas is expanding under isothermal reversible conditions compared to that when the gas is expanding against reversible adiabatic conditions. Otherwise also, if the process is isothermal means the temperature is being kept constant. Therefore, the internal energy of the system is continuously being replenished, and hence the system can do more work. Whereas, in an adiabatic process, the internal energy decreases. Therefore, the work available from the system will be less. Let us look at one of its application in the form of this question. A sample of 3 mole of a gas at 200 Kelvin and 2 atmosphere is compressed reversibly and adiabatically until the temperature reaches 250 Kelvin. Given that its molar constant volume heat capacity is 27.5 joules per Kelvin per mole, calculate Q, W, delta T, delta U, delta H and the final pressure and volume. So, many quantities need to be calculated. However, as I expressed earlier also, that we can straight away start with the first law of thermodynamics, delta U is equal to Q plus W. And since the process is adiabatic, Q is equal to 0, therefore, delta U is equal to W. So, when we calculate delta U, then we do not need to calculate W through P and V, because delta U will be equal to W, and let us see how to calculate that. Let us take a look at the slide. Adiabatic process, Q is equal to 0. So, therefore, delta U has to be equal to W. We can use again here the definition of heat capacity Cv, which is dou U by dou T at constant volume, which will give us delta U, which is equal to N times Cvm times delta T, and it has to be equal to work by the arguments given above. Now, you substitute the numbers, N is 3 mole, Cvm is given 27.5 joules per Kelvin per mole, temperatures are also given 250 and 200 Kelvins as the final and initial temperature, and this turns out to be 4.1 kilojoule. Next, we need the final volume, and final volume can be calculated from this expression, because you remember we just showed that V I T I raised to the power C is equal to V F T F raised to the power C, and if we rearrange that, we will have this expression V f is equal to T f by T I raised to the power C m by R into V I. V I can be calculated from N R T I by P I, because this is an ideal gas. And once we substitute all the numbers with a suitable value of R in liter atmosphere per Kelvin per mole, the volume comes out to be 11.8 liter. This is the final volume. Then immediately, if I know the final volume, and since it is an ideal gas, I can calculate P f, which is equal to N R T f by V I. This is 5.2 bar. Now, the only thing that is left over is to calculate the change in enthalpy, and change in enthalpy again we can calculate from this expression, delta H is equal to delta U plus N R delta T, and here we have the value of delta U we have already calculated. We know the value of N R delta T, you substitute the numbers, and here I am converting joules into kilojoules by dividing by 1000, the number comes out to be 5.4 kilojoules. So, the way to solve these type of questions when the process is adiabatic, it is always a good idea to start with the first law of thermodynamics, and then to see how we can use the different definitions to get the answers for the various thermodynamic quantities that have been asked. So, in this lecture we discussed how to calculate the work done in an adiabatic process. We discussed that we actually do not need to work through pressure and volume, we can work through the changes in internal energy, because Q is equal to 0. And then once we know the changes in internal energy, we can get the other thermodynamic quantities. We will discuss more in terms of numerical problems in the future lectures, and if there are any questions or queries, we will discuss those in the help session. Thank you very much.